Okay, so for today, we're going to go through two chapters. One is atomic structure, which is more of a revision. So this was covered actually in Sec 1. Okay, so Sec 1, we have actually covered this. So we're going to recap a little bit on this as a revision. Okay, then we're going to go on to do chemical bonding. So that will be for today. Okay, so let's start. Okay, so atomic structure, in terms of what is really inside the atom itself. So we know that an atom is made out of the three main subatomic particles. Okay, what are these three main subatomic particles? They're actually your protons, neutrons, and electrons. Now, your protons and neutrons are in the middle. So proton and neutrons are actually in the middle. Okay, those in the middle actually has mass. So you realize for proton and neutron, okay, the relative mass is 1, okay, because they're in the middle. So what contributes to the mass of an atom actually is the particles in the middle, which is the proton and the neutron. Okay, you look at the relative mass of an electron is 1/1840. So it's very, very light because you know that an electron is actually circling around the nucleus. Okay, so that's why it needs to be very, very light. Now, in terms of the charge, proton, from the word proton, you know that it should be +1. So there's a relative charge of proton. A neutron has a relative charge of 0 because neutron, think of it as neutral. And lastly, electrons. Okay, now, because the proton is +1, the electron should be -1. This will actually allow you to have the kind of traction to keep the electrons circling and close to the nucleus. Okay, so the electrons don't actually run off. Okay, so electrons has a charge of -1. Okay, so we have a symbol of P, N, and E. P for proton, N for neutron, E for electron. Okay, so a little summary is over here. Now, this table actually came out in your Sec 1 end of year exam before. I can safely say that it may come out again in your end of year or even for your WA3. So this table here, please take note of it. Okay, most people will tend to be confused between the relative charge and the relative mass. So you must be very clear in terms of charge, in terms of mass. Charge is the one that you have your plus and minuses. Mass is the one that you're going to have this 1/1840. Okay, so that's the first part here in terms of the three main particles that makes up your atom. Okay, next we're going to go on into the proton and the nucleon numbers. Okay, nucleon and proton. Now, take note, this is not neutron number. Okay, so this is actually a nucleon number. Okay, we're going to go a little bit into details here now. Okay, this next whole part here, we're going to look at what is the proton number, the nucleon number. Okay, after that, we're going to learn how to be able to determine the P, the E, and the N of an atom. Okay, and lastly, we're going to learn how to interpret and use symbol to represent an element's nucleon and proton number. Now, for those of you who feels that I'm going a little bit fast, okay, why is it so? It's really because this is revision for your Sec 1 stuff. Okay, so it's a bit of a recap. I need all these little details over here in this chapter so that we're able to go more in depth in the next part, which is chemical bonding. Okay, so this is the atomic structure of helium, lithium, and beryllium. So based on what you can see, okay, helium is made out of 2 protons, 2 electrons, 2 neutrons. Lithium, what you see is actually there's 3 protons, 3 electrons, okay, and then 4 neutrons. Now, in case you're thinking, how come I know? So we know that green is neutron, we know that purple is proton, and the light blue is electron. So it's literally just counting off from here. Okay, that's how they go about this. Now, I want you to put one star over here and just take note. Atoms of different elements have different number of protons. What does this mean? Okay, so I'm going to refer to you to the periodic table that you're going to receive all the time. Now, the top number, okay, the top number here, okay, this is actually the proton number. What you realize is that every single element has a different proton number. Okay, so the proton number actually tells you, okay, actually tells you what element it is. So this one I already mentioned before already. So just keep it in your mind, take note of it. Okay, now next. One thing they want to highlight is this. It is that for an atom, the number of electrons is the same as the number of protons. So the proton and the electrons are the same for an atom. Okay, for an atom, the number of protons and the number of electrons is the same. Okay, why is it so? It's because the negative charge will actually cancel out the positive charges. So the negative charge is your electrons, the positive charge is your proton. So because once they cancel out, we say that the atom is electrically neutral. Okay, this term of electrically neutral actually just means that the proton must be equal to the electrons. So you realize this whole paragraph is just describing this over and over again. Okay, so for atoms, proton is equal to the electron. Okay, as what you can see here. Next, what is the proton number? So obviously the word proton number tells you that it's the number of protons in the atom. Now, do take note to a star over here. Another name for proton number is also called the atomic number. Okay, another name for the proton number is also called the atomic number. And since atoms are electrically neutral, the proton number can also tell us the number of electrons. Okay, so let me give you an example. Let's say, for example, I got lithium 37. This 3 over here, the smaller number is always the proton number. So quick recap, we can find out what is the P and E, the proton and electrons for this. Because why? Lithium, the proton number is 3, means that it has 3 protons. How many electrons will lithium atom have? It will also have 3 electrons. Why both the same? Because we know for an atom, the P is equals to the E. Right? The P is equals to the E because it is electrically neutral. So just remember this. Okay, quick recap. Next part, we're going to go into this idea called the nucleon number. Okay, the nucleon number is actually the total number of protons and neutrons in an atom. Okay, the nucleon number is also called the mass number. And why is it so? Because the mass of an atom is actually dependent on the number of protons and neutrons, okay, as indicated over here. So how do we go about using this information? So I go back to the idea of lithium again. Lithium is 37. So for a lithium atom, P, E, and N, proton is 3, electron is 3. We already determined just now. This number 7 here is actually the proton plus neutron. The proton number here is a proton. So how to determine the number of neutrons is to take the top number, the nucleon number, minus the proton number. This will actually give me the number of neutrons. So in this case here, the number of neutrons here will be 7 minus 3. This will be equals to 4. Right? This will be equals to 4. So do take note of this one over here. You must be able to calculate the PEN for all your atoms. Okay, this is the most basic thing you must know. Okay, if you don't know this, you're going to face a lot of issues when you go into chemical bonding. Okay, so typically representing a proton and neutron number, you realize the proton number will be at the bottom, the nucleon number at the top. So just like what I wrote just now, Li37. Now, I want you to refer back to the periodic table. Okay, if you look at your textbook or you look at my one over here, which is the one that you always see, you realize the difference between your, the chemical symbol and the periodic table is that you realize that, hey, how come the smaller number is on top, the bigger number is at the bottom for the periodic table? But when you draw it, when you write it out, how come the chemical symbol, the smaller number is at the bottom, the bigger number is at the top? Okay, so just take note, there is a difference between your periodic table's chemical symbol, okay, the way how we represent the proton and the neutrons, versus the one that we normally would draw. So some of you may be confused, so is it the top number or is it the bottom number that's going to be number of protons? So I just want you to take note. So for a star here, the smaller number will always be equals to the proton number. Okay? The bigger number will then always be equals to the nucleon number. Okay, so take note of this part over here. Okay, this will at least help to prevent some confusion. So if I go back to my periodic table, let's say maybe I use calcium. So calcium, you can see 20 at the top, bottom is 40. How would I write the chemical symbol? It's actually like this. Okay, so you look at I want you to compare and contrast. This one is the chemical this is what is written in the periodic table. But whenever you're writing the chemical symbol, proton number always at the bottom left, the nucleon number always at the top left. Okay, so that is this part over here. So maybe just to help everyone consolidate this part here, so maybe we can do two different examples. Sodium 1123. The other one we can try would be maybe aluminium 1327. Okay, so where did I get these two numbers from? It's actually over here. So you can see aluminium 1327. You can see sodium 1123. Okay, so how many proton, electron, and neutron does sodium have? How many proton, electron, and neutron does aluminium have? So this one, I'll give you 5 seconds to just do your mental calculation before I go through it. So 5, 4, 3, 2, 1. Okay, so let's go through sodium. Sodium, the bottom number here is 11. So number of protons is 11. Because this is an atom, I'm looking at the atom itself. So we know that it's electrically neutral. So proton equals to electron. The neutron, number of neutrons here is actually taking the bigger number minus the smaller number, we're going to get 12. So same thing for aluminium, proton is 13, electron is 13, neutron would be 14. Yes.
Are you going through the whole topic today?
Going through the whole atomic structure and chemical bonding.
Yeah.
Okay, anyway, please mute yourself, because I'm recording the session.
Okay.
Okay, so that will be for how you're going to get number of protons, electrons, and neutrons. Next, we're going to go into this concept called isotopes. Okay, what are isotopes? Okay, before we go into the definition, I just want to show you, okay, two isotopes. My classic example that I like to give is oxygen, 816. This is the one that you see in your periodic table, oxygen 816. Okay, the other one will be oxygen 815. Okay, so I will tell you that these two are isotopes. Okay, these two are isotopes of oxygen. Now, how do I know they're isotopes? What exactly are they? So first thing, before we go into what is the definition of isotopes, let's count the P, E, and N. So for oxygen here, we got 8 protons, 8 electrons, 8 neutrons, 16 minus 8. For this one over here, PEN, we got 8 protons, 8 electrons, but we have 7 neutrons. So what exactly are isotopes? If I say these two are isotopes, what do you realize about them? They are atoms, okay, because the P equals to the E. They are the same elements, so they are atoms of the same element, okay? What else do you see? They have the same number of protons, same number of electrons. But what you realize about the neutrons is that they are different. So isotopes are actually atoms of the same element. So take note of the S here. So when you talk about isotopes, you must always have at least 2 atoms of the same element that you're comparing. Okay, so the atoms of the same element with the same number of protons, electrons, but different number of neutrons. So another example is chlorine 35 and chlorine 37. Example, what is 35, 37 here is actually Cl 1735. This is actually Cl 1737. Okay. Now, if I were to ask you, can you give me another isotope of chlorine? Okay, suggest what is another isotope of chlorine? Actually, it's just very simple. You got 35, 37. Another possible can be Cl 1736. You realize the proton number must always be the same, because the proton number tells you what element it is. So all 3 are atoms of chlorine. That's why the bottom number, which is the number of protons, must be the same. Then how do I indicate that they have different number of neutrons? I just change the nucleon number. Okay, so chlorine 35, chlorine 36, chlorine 37. These are the various isotopes of chlorine. Okay? Now, so some of the interesting facts about it is that isotopes have same chemical properties but slightly different physical properties. So same chemical properties means that they have the same reaction. All of them will undergo the same type of reaction. So whenever you see chemical properties, we are referring to the term reactions. Okay, but they have slightly different physical properties. So one example of physical properties they actually can talk about in terms of boiling point and melting point, can be in terms of density, okay, can be in terms of mass also as well. Okay, so these are some of the examples of your physical properties. Okay, so isotopes, do take note, same number of protons and electrons, a different number of neutrons. What's the use of isotopes? Okay, this one you can, sorry, I should put stuff here. Go and read up on your own. I don't want to go through this one. This one just going to read up. But do you have to memorize all this? Don't need to memorize. Don't need to memorize. Okay, just in case you think church must memorize. Don't need. Okay. Okay, next. Arrangement of electrons in atoms. So we have learned how to determine the number of protons, electrons, and neutrons in an element, okay, in an atom of an element. Now we're going to look at in terms of how do we arrange, okay, arrange the electrons. Okay, now question is, so why not talk about the arrangement of protons or the arrangement of neutrons? But it's really because the nucleus have no specific arrangement. Okay, or more like we don't really need you to go and learn that. It's not your syllabus. So the nucleus have no specific arrangement for your proton and neutron. So that's why we just clumped all the proton and neutron in the middle of your atom. But we don't really say like, oh, must alternate the proton and neutron and stuff like that. Okay, we don't really say that. We just say everything's in the middle. The only one that we actually will pay more attention to is in terms of the arrangement of the electrons. So how exactly are the electrons arranged? Okay, now why is it important to know is really because knowing the arrangement of electrons will actually determine the chemical properties of an atom. As mentioned, whenever you see the word chemical properties, you think of reaction. So how the electrons are arranged actually determine the reactions that the atom will undergo. Okay. Now, how are electrons arranged? They are arranged in terms of electron shells. Okay, so there's first shell, second shell, third shell. Okay, each shell is a sort of like specific energy level. Just know that the closer it is, the lower the energy level. The further away, the higher the energy level. Okay, they can only hold up to a specific number of electrons. So the first shell can only hold 2 electrons. So the max that the first shell can hold is 2 electrons. The second shell is 8 electrons. The third shell, okay, 8 electrons, so on and so forth. So do take note that in your syllabus, we'll just take it as first shell can hold 2 electrons. Subsequent shells, okay, all of them will just be able to hold maximum 8 electrons. Okay, so now let's look at in terms of the electronic arrangement. So for magnesium atom, okay, you look at it, the nucleus, they draw one circle, shaded it like this, and then they right here, 12p plus 12n. Okay, this is actually the atomic structure. This is atomic structure of magnesium. Okay, now magnesium, in terms of magnesium is actually Mg1224. So in terms of PEN, I got 12 protons, 12 electrons, 12 neutrons. So in the middle, I got my 12 protons, 12 electrons. Okay, sorry, 12 protons, 12 neutrons. Okay, then I'm left with 12 electrons. How are the 12 electrons exactly arranged? So first thing, okay, just a quick recap. First shell can only hold 2. So if I've got 12 electrons, my first shell, I hold 2 electrons, I'm left with 10. Then of course, 10 must go into the second shell, right? Now, the second shell maximum we mentioned can only hold 8 electrons. So therefore, I pump in another 8 electrons here. I'm left with 2 electrons. And hence my third shell, I'll pump the rest in. That's why the electronic configuration is 2, 8, 2. First shell maximum 2, second shell maximum 8. The remaining amount will now go to the third electron shell. So the electronic configuration is 282. Okay, now there's a new term we want you to take note of. It's called the valence electrons. So the valence electrons is actually just the electrons in the outer shell. So if you look at the description here, they say the valence shell or the outer shell, okay, refers to the shell that's the furthest away from the nucleus of the atom. Okay, so if I look at this here, okay, I'm going to use a different color now. This is my first shell. This is my second shell. This is my third shell. So the third shell is the electron shell that's furthest away from the nucleus. This electron and these electrons are what we call the valence electrons. Okay? Why are they called the valence electrons? Because they are the electrons on the furthest shell. Okay? Or I should say they are electrons on the outer shell. So take note, electrons in outer shell, we call them valence electrons. Okay? So sometimes when you do bonding, you realize that they'll ask you to draw only the valence electrons. Okay, so this is an example of it. Now, this is something that is you're going to learn more in detail in the subsequent chapter. But before that, I thought this is actually quite an interesting one to take note of because it's going to help you to find the elements better. Now, in the periodic table, elements are arranged in order of increasing proton number. What do they mean? It's really, for example, if I say element number 20, you can actually just count. Element 1, element 2, element 3, 4, 5, 6, 7, 8, 9, 10. Okay, all the way, element 20 will be calcium. Okay, so they are all arranged in increasing proton number. So you realize the proton number will just keep increasing one by one. Okay, so that's what they mean by the periodic table's elements are arranged in order of increasing proton number. Now, to help everyone identify the elements faster also, so they are arranged in what we call periods and groups. So periods is the horizontal row, groups are the vertical columns. So go back to here, you realize there's a word group over here. So how many groups are there in the periodic table? There's group 1. Okay, let me use a different color. There's group 1. Sorry, group 1. Group 2. Okay, so these are all in Roman numerals. Group 3, group 4, group 5, group 6, group 7, and group 0. So in total, there are 8 groups. Okay, there are 8 groups. Then in terms of the row, how many rows are there? They say that there are 7 rows. So if you look at it, okay, most people will confuse, they will think this is row 1. Wrong, wrong. Okay, this is not row 1. Row 1 is actually over here. This is row 1. Right? Because there's hydrogen, there's helium over here. Right? Then there's row 2, row 3, row 4, row 5, row 6, row 7. So 7 rows over here. So there are total 8 groups and 7 rows. Right? That's your periodic table. Now, do take note, okay, the bottom here, they got all the 20 elements drawn. Okay, so you can see the electronic configuration all drawn here. Now, I just need to take note of this. Normally, when you draw the electronic configuration, in the middle, we will not put a circle like this. Okay, what we'll normally do is in the middle, we'll write the chemical symbol. So, example, if I want to redraw helium, so this will actually be drawn as He, then one dot over here, one dot over here. Okay, so you can use dot to represent electrons. Now, there's another way to represent electrons as well. So let me now use carbon to show you. So the middle, I can change it to a C. Okay, there are 2 shells, first shell, second shell. So first shell, I have 2. Second shell, I have 8. Second shell, I have 4. Okay, 1, 2, 3, 4. So I can use cross to represent my electrons as well. So take note, it can either be dot or it can be cross to represent your electrons. So, but take note, in the middle, we normally will not draw this circle as mentioned just now. We will use the chemical symbol itself. So it's carbon, we'll put the capital C. If it's helium, we'll put He. okay, and etc. So take note, they have all drawn all this for you, but you must be able to decipher what's the electronic configuration on your own. So just to give you a quick example, maybe like just now, we actually saw potassium. Potassium is 1939. If I go by PEN, it's 19, 19, 20. To think of the electronic, to know what's the electronic configuration, I focus on the electrons. Okay, so if I got 19 electrons, think of it as first shell, I can put 2, I'm left with 17. Second shell, I can put 8, I'm left with 9. Third shell, I can put another 8, I'm left with 1. And this 1 will actually come over here. So you realize what is at the bottom here is the leftover electrons that I need to fill up. That I need to fill up into my electron shells. So once you're done with the working here, you cancel all this. This is your electronic configuration. Electronic config. Okay, now think about electronic configuration. These two, the drawing one and the writing one, 2881, these two are called electronic configurations. But this one is actually the written form. Right? This is the written form. So I want you to write the electronic configuration, you write 2881. But if you want to draw, okay, this is the drawing way. So drawing and writing, both also can. Really depend on what the question wants. Okay, so that is the electronic configuration part. Right, so actually that marks the end for atomic structure as a revision. So right now, half an hour has passed. I want to pause this segment over here now. Okay, everyone just go and take a quick breather for 1 minute. Then I will zoom in into chemical bonding. Okay, so I'm going to pause the recording now. Okay, so let's go on now to chemical bonding. At this point, I will now go a little bit slower because this is no longer revision. This one is really going through the topic way that you are currently going through. Okay, now, so let's start off in terms of chemical bonding. Okay, you realize they start off with this idea of the stable electronic configuration of a noble gas. So, what is this starting thing all about? Okay, now I want you to take note of this. So, key idea here is all elements, okay, want to be stable. Okay, all elements want to be stable. Okay, however, not all of them start off naturally as being stable. So the question is, when you say all elements want to be stable, what do you mean by stable? How can an element become stable? So they can become stable if they have what we call the noble gas electronic structure. So I say again, all elements can become stable if they have this thing called the noble gas electronic structure. So what exactly is this noble gas electronic structure? So that's where we started to look into what we call the noble gases. So we see that all noble gas actually have an electronic configuration that is stable. So why are they stable? So we're going to look into that. Okay, so let's start off. Noble gases are what we have here, helium, neon, blah, 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 blah. Where can we find noble gases? These are all the noble gases. Okay, all your group 0 elements are your noble gases. Okay, now, do take note, the noble gases do not react with other elements or form compounds. Okay, they are usually monatomic and exist as individual atoms. Why is it like this? Okay, why are noble gases like this? It's really because they are unreactive, they are stable. So question is, why are they unreactive? Why are they stable? As mentioned just now, is because they have what we call the noble gas electronic structure. Okay, noble gas electronic structure. Whereas atoms of most other elements are reactive, they combine with other atoms to form compounds because they do not have the noble gas electronic structure. Then of course now this is where you will start to ask, what do you mean by noble gas electronic structure? Okay, I mean you tell me noble gas electronic structure applies to noble gas, okay lah. Other elements can also get noble gas electronic structure, man. Okay, the answer is yes. So first thing, before we even talk about how other elements get the noble gas electronic structure, we need to understand what it means by the noble gas electronic structure. So let's look at the outer shell. Okay, helium only got one shell actually. Helium only got one shell. And the first shell, you realize it has 2 electrons. So the first shell is fully filled. Look at neon. The outer shell got 8 electrons. So 8 electrons, fully filled. That means my valence shell, my outermost shell is fully filled. Same, you realize here 8 electrons, 8 electrons, 8 electrons, 8 electrons. Okay, this one we call them octet electronic configuration. This one I call it duplet. Now, instead of thinking of octet and duplet, I just want you to think of it as all of this, okay, all of them, all of the elements here, their valence electrons, their valence shell is fully filled. Remember we did say valence shell means what? It means it's the outer shell, outermost shell. So the outermost shell is fully filled. Right? Outermost shell is fully filled. Okay, so like what you can see here, noble gases are unreactive because they're fully filled outer shell, or fully filled, instead of the word outer, I use the word valence shell. Okay, this is what makes noble gases so stable, is because their valence shell is fully filled. So once over here, take note of this. So how do other atoms, okay, how do other atoms, why I use the word other atoms? Because initially we're talking about noble gases. So if we know all noble gases have the valence shell fully filled, then how about other atoms? So other atoms can also achieve the noble gas electronic structure. Okay, how do they do so? Okay, now, so take note, they say here, right? Atoms of elements, except for noble gas, they do not have fully filled outer shells. So that's why they are reactive. Right? Those of you who don't never read your textbook, actually realize, teacher, this one explained quite okay, understand, Okay, so they are reactive because their shell is not fully filled. So the next question that we will ask is this, okay, how can they have this noble gas electronic structure? So these atoms actually undergo reactions, okay, to achieve this stable electronic configuration. How do they do so? They will either lose electrons, gain electrons, or they will share electrons. Now, so this lose, gain, and share is actually very important. This part over here, losing and gaining, is actually the concept of ionic bonding. Okay, in your syllabus, that's actually your ionic bonding. Sharing of your electrons is actually your covalent bonding. Okay, so this is why this chapter is called chemical bonding, because we're gonna learn about how the atoms become stable by undergoing bonding. So once over here, atoms become more stable by undergoing bonding. Right? By undergoing bonding. Wow. Now, at the end of bonding, what actually happens is that by undergoing bonding to achieve its valence, to have its valence shell fully filled. Okay, so really key idea here, why bonding is really so that the outermost electron shell, or we call it the valence shell, would become fully filled. Okay, how do? They undergo ionic bonding, or they can undergo covalent bonding. So let's start the first part here. So in terms of forming ions, we are really jumping into the concept of ionic bonding. Okay, so those of you whose bonding not so clear one, okay, I hope you understand at least the basics of it is that why do atoms bond? Right? Atoms bond so that they can have their valence shell fully filled. Okay, so recall from chapter 5, atoms have equal number of protons and electrons. Okay, so atoms have equal number of protons and electrons. We call them electrically neutral. Now, but when the atoms undergo bonding, they will no longer be electrically neutral now. Okay, so an atom becomes an ion when they lose or gain electrons. Okay, so I say now, an atom becomes an ion when they lose or gain electron. Now, when you lose and gain electron, what you realize is that the proton will no longer be equals to the electrons. Okay, and when the proton is no longer equals to the electrons, we term them as ions. Okay, ions. Now, put a star over here. Now, metals tend to form positively charged ions, which we call cations. Non-metals form negatively charged ions, which we call anions. So positive, we will call it cations, and they are typically made of metals. Negative, we call them anions. They are typically non-metals. Okay, so let's start by focusing on the cations itself. Okay, so atoms of metals generally only have a few outer electrons, thus they tend to lose electrons to form cations. So metal tend to lose electrons to form cations. Okay, when they lose electrons, they have more proton than electrons. That's why we have a positive ion over here. Okay, that's why they form positive ions. So take note, put a star over here. Positive ions or cations are formed when atom loses electrons. Okay, take note, it is not gain proton, it's lose electrons. In this whole process here, we were just only looking at lose electrons, or we will think in terms of gain electrons. The protons in no way are going to change. Okay, I say again, the protons are in no way going to change. It's only the electrons going to be more or less because it's either they lose or they gain electron. So for positive ion, they will lose electrons. Okay, so cancel the gain here because gain is for non-metals. Now, so let's look at figure 6.2 and 6.3 over here. 6.2. Now, look at this here. The drawing. So a sodium atom has 11 protons, hence it will have 11 electrons. The electronic configuration is 281. 281. Now, is sodium atom stable? Answer is no. Okay, it is not stable. Okay, it is actually reactive. Okay, so sodium atom is actually not stable, it's actually quite reactive. So how does it become stable? How can it have its valence shell fully filled? So think of it this way. Now, for the sodium atom to have its valence shell fully filled, there's two ways. One is 2, 8, 8. The other one is it can become 2, 8. How to become 2, 8, 8? This one, I must plus 7 electrons, right? This one here, I must minus 1 electron. So sodium atom, there's two ways for it to get its valence shell fully filled. It's either I gain 7 and I become 288, or I will lose 1 and become 28. Obviously, we think in terms of it, right? Which one is easier to become stable? It's definitely a lot easier to lose 1 electron instead of gaining 7. As such, gaining 7 electrons actually don't exist. So the sodium atom will actually lose 1 electron, as mentioned here, to become 28. Now, what you realize is that from this diagram to this shell has disappeared. This shell has disappeared, correct? The third shell has disappeared. What else do you realize is that now, because it's an ion, you draw a square bracket, okay, around it. And because it lost 1 electron, you put a plus over here. And you put a plus over here. Okay, now let's go on to the next one. Okay, then we will compare and contrast a little bit more. So magnesium, 12 proton, 12 electrons, 282. So once again, you can either gain 6 electrons or I can lose 2 electrons. What do I mean by that? Okay, so I'm going to do the exact same kind of drawing here. So what can magnesium do? It can either plus 6 electrons to give me 288, or it can lose 2 electrons to give me 28. If you think carefully, obviously, is this rubbish to gain 6 electrons because it takes a lot of effort. So therefore, losing 2 electrons is actually the way of how magnesium becomes stable. Okay, it actually doesn't gain 6 electrons. You actually lose 2 electrons to become stable. As such, what you realize in terms of the drawing, okay, the 2 electrons is lost, so the outer shell disappears. And because I lost 2 electrons, it becomes an ion, right? Whenever you go ion, you will draw this square bracket. If I lose 2 electrons, I'm going to become 2 plus. Okay, lose 2 electrons, it becomes 2 plus. Okay, okay. Now, I want us to look at another example over here. Last one is actually aluminium 1327. So the electronic configuration is actually 283. I just shortcut, just so you go into it now. Electronic configuration of aluminium is actually 283. So what will happen to aluminium when it undergoes bonding? So obviously, when you look at 283, it wants its valence shell to be fully filled, right? So in the process of bonding, it's going to lose 3 electrons. I'm going to get 2, 8. And because I lost 3 electrons, aluminium actually becomes Al 3 plus. It is actually Al 3 plus. If I were to draw it out, Al in the middle, first shell will have 2 electrons, second shell will have 8. Okay, that's all. But because it's an ion, I need to put a square bracket, and then I put 3 plus. So that's how you go about drawing ions. Okay, that's how you go about drawing ions. So why do atoms undergo bonding? Back to the original idea, they want to have its valence shell fully filled. And they can either lose electrons or gain electrons. Okay, so for metals, they tend to lose electrons. Now, next one, we're going to look at how do atoms become negative ions. Okay, so non-metals generally have more than 4 outer electrons. So they tend to gain electrons. So non-metal tend to gain electrons to form anions. Okay, once they gain, they will achieve the electronic configuration of a noble gas. Now, because it gained electron, right? So now there are more electrons than protons. Therefore, a negative ion is formed. So take note to us over here. Negative ions or anions are formed when atom gains electrons. Okay, so let's go through some example now. Chlorine atom, 17 protons, 17 electrons. Electronic configuration, 287. So that's what we have here. Now, 287, there's 2 ways that it can undergo bonding. One is plus 1 electron to become 288. The other one is minus 7 electron to give me 28. Now, think in terms of quantity, sheer quantity. Is it easier to gain 1 or to lose 7? Obviously, gaining 1, the process is a lot faster, a lot better, comparing to losing 7 electrons. And hence, this is not the way to go out. It doesn't lose 7 electrons, instead only gain 1 electron. So therefore, in this case here, because it gained 1 electron, it becomes Cl minus. Now, I want you to take note in the diagram here. I want you to convert one of this circle into an X. Why did I want to change one of them to X? Okay, initially, the outer shell has 7 electrons. So you count the blue dots. There are actually 7 blue dots over here. 1, 2, 3, 4, 5, 6, 7. Okay, so for the last electron, okay, because it is gained from somewhere else, I will tend to show an X. I'll use X to represent it so that it is very clear that this electron came from somewhere else. And because this is now an ion, you must always have that square bracket. Because you gain 1 electron, it becomes a minus. Okay, this is actually your Cl minus ion. For oxygen, okay, 8 proton, 8 electrons. So electronic configuration 2, 6. So 2, 6 over here. Now, once again, go back to the same idea. I can either gain 2 electrons or I can lose 6 electrons to give me 2 or to give me 2, 8. Which one is easier? Obviously, it's easier to gain 2 compared to losing 6. Therefore, because I gain 2 electrons, okay, I'll become 2, 8 like this. Now, as mentioned at the top, because it gained 2 electrons, we're going to show that 2 of the electrons is gained from elsewhere. So I'll change 2 of the dots to a cross. Next, because it's gained 2 electrons, it's an ion now, so I will put a square bracket. And because it's 2 electrons gained, I'll put a 2 minus. Okay, now, common mistake people tend to have is that they always confuse whether I should write a plus or should write a minus. Do take note, plus is when lose electron, minus is when they gain electron. Okay, so you must be very clear on this, huh? Very, very clear on this. Okay, now, these are some of the common ions and their charges. Some of it is harder for you to remember. Okay, example will be this. Actually, I'll tell you what. Those that is harder to remember, I'm going to put a star there. Okay. Okay, so this that I put stars, okay, I'll explain to you why they are harder to remember. Okay, now, it's really because, right, for sodium, potassium, hydrogen, calcium, all this, it's actually very easy to determine. Now, one in your periodic table, right? Okay, whenever you got periodic table now, this is one thing I want you to write every single time once you get it. So every time when you get a fresh periodic table, always write down this number over here. Above your group, you write 1, 2, 3, 4, 3, 2, 1, 0. Okay, this is what I call the bonding number. Okay, in books, they will call it valency. Okay, you don't need to know the exact term of this 1, 2, 3, 4, 3, 2, 1, 0. But these numbers are going to be very, very helpful. How helpful are they? Very simple. So for lithium, Li, okay, so I'm going to show you how. Let's use the notes. So for lithium, okay, if you go and check, lithium is in group 1. The bonding number is 1. So how will the bonding number help me? So if lithium is a metal, the bonding number, I put Bn, Bn is 1. What does it mean? Metal means that it will lose electron. How many electrons will it lose? Focus on the bonding number, 1 electron. So therefore, lithium will actually lose 1 electron. And when I lose 1 electron, it's going to become a Li plus. Okay? So that's how you go about using the bonding number. Let me give you another example. So maybe I will use aluminium. Aluminium over here. Just now, actually, we did the drawing version of it. But now let's use the bonding number. Okay, aluminium is a metal. The bonding number for aluminium is 3. So because it's a metal, it will tend to lose electron. Because its bonding number is 3, we know that 3 electrons will be involved. So therefore, we know aluminium tend to lose 3 electrons. So we get Al3 plus. So the bonding number is very, very, very useful. It's going to help you to determine quite a fair bit of things. Then, of course, next is you say, does this bonding number also help me for my non-metals? Yes, it does. So let's look at maybe, for example, fluorine. Fluorine is bonding number 1. So fluorine is a non-metal. So I put Nm for not, sorry. Let me just write that. Fluorine is a non-metal. The bonding number is 1. So because it's a non-metal, it tends to gain electrons. The bonding number is 1. So obviously 1 electron is involved in doing bonding. So because it's a non-metal, bonding number is 1. Fluorine tend to gain 1 electron. So when fluorine gain 1 electron, it becomes F minus. So you're going to draw F minus. Okay. Maybe now we can try oxygen. Oxygen is a non-metal. So it will be gain electron. Periodic table, go back to it. Oxygen, group 6. Bonding number is 2. Okay, so bonding number is 2. So what it means is that the number of electrons involved during bonding is 2 electrons. So oxygen, because it's non-metal, it will gain 2 electrons. Hence, it will become a O2 minus. Okay, so this is a very simple way of helping yourself to know what should be the charge of the ion, how many electrons it will gain, how many electrons it will lose. Okay, so the periodic table is a very, very useful tool. In case some of you forget, thinking, where's the metal, where's the non-metal? So draw a line like this. Okay. So this is the staircase line here. Everything on this end is non-metal. Everything on the other end is metal. Okay, so hydrogen is an interesting one. Okay, hydrogen is an interesting one because you realize for hydrogen, you'll say, hydrogen never belong to anywhere, leh. So for hydrogen, I want you to park it at group 1. So imagine hydrogen is over here. Just park hydrogen over here. So hydrogen, take it as a macam group 1, bonding number 1. Can? Okay, but it is a non-metal. So just think of it, it's a non-metal. Okay. Actually a bit of a metal, forget it. Hydrogen is a very special element. I will later explain to you a little bit more. Okay. So going back to here, realize Na plus, K plus. Okay. It can be found here. Na, bonding number 1, so that's why it's Na plus. K plus, because it's a metal, bonding number is 1. Next one, calcium, Ca2 plus. How you know it's Ca2 plus is because calcium is a metal, it's in group 2. So calcium will give you, calcium bonding number is 2, so calcium will actually form a 2 plus. Okay, calcium will actually form a 2 plus. So just take note of that. Now, how about the rest? Okay, the rest of it, copper, can you see there's a 2 here? That's why it's a 2 plus. Iron 2, 2 plus. Iron 3, 3 plus. Chromium, 3, 3 plus. So if you're lucky to have this, this Roman numerals there, these Roman numerals actually tell you what is the charge of the ions. Okay, hydrogen, this one, go remember. Now for silver and zinc, why do I put a star there? It's really because, can you see zinc is here? Silver is over here. There's no bonding number, there's nothing above it. So you can't really determine the charge because there's no bonding number given. And so you must memorize for zinc is 2 plus, for silver is Ag plus. Ammonium is NH4 plus. Okay, so this one is the interesting one. They already say the cations are usually metals, but for hydrogen ions and ammonium ions are some exceptions. So obviously, once you see exceptions in chemistry, please go remember. Okay, please go remember. Okay, non-metals, I think this one don't go through too much. Hydride, normally not in your syllabus, so you can ignore it. But if you go and do pure chem, hydride, you need to know. Now, most people will have issues with this 3 plus this one here. Hydroxide, nitrate, carbonate, and sulfate. Okay, once you see ATE, remember I told you before, it means that they must have oxygen within them. So this few you must get familiar, which is a nitrate, which is your NO3 minus, carbonate, which is CO3 2 minus. The last one is your sulfate, SO4 2 minus. Okay, this one will really come in very handy, especially when you go up to Sec 3. Okay, so for now, just know them, okay? But when you go to Sec 3, you must be very, very familiar with them. Okay, so this is actually how the ammonium, carbonate, and sulfate ion looks like. Okay, this is what we call polyatomic ions because they are ions. Because they are ions that comprises of 2 or more covalently bonded atoms. So these are the interesting ones because it feels like, covalent also equals to ionic. Or covalent can also form ionic. This one was exclamation mark. Pure chem, we'll cover a bit more. Huh? Okay, for now, don't need to worry too much. Okay, I say again, this part here, don't need to worry too much for now. But you need to know this, you need to know this. Okay, so that is for formation of ions, cation and anion. Now, so the interesting thing is this, okay, how did my ions become positive? How did my ions become negative? Right, so you look at this diagram over here, as much as it's a bit lame, but sodium atom is initially 281. Chlorine atom is originally 287. So do you realize that sodium want to lose one electron? Chlorine want to gain one electron. So bonding only occurs, okay, I should say that the atoms only lose or gain electrons when they have a partner. Okay, I say again, the bonding only occurs when the atoms have partners, where I have one person who wants to lose electrons, another atom that wants to gain electrons. Okay, and this type of reaction, okay, we actually call it ionic bonding. Now, what exactly happens and what is it about ionic bonding? So take note, when a metal reacts with a non-metal, okay, what is going to happen is that the metal atoms will actually transfer their outer electrons to the non-metal. This transference of electrons is actually called ionic bonding. Right? This transference of electrons is actually called ionic bonding. Okay? Now, after ionic bonding, you have an Na plus and you have a Cl minus, example over here. Now, because one of them is plus, one of them is minus, they will actually attract each other. Okay? And this attraction is what we call the ionic bond. So the ionic bond is the strong electrostatic force of attraction. Electrostatic just means electrical charges. Electrical charge. Right? Electrostatic force of attraction between positive and negative ions. Okay, and compounds with ionic bonds, we call them ionic compounds. Okay, now, pause here first. I need you to take note. Whenever you see the word ionic compound, few things must come to your mind. First thing is about transfer electrons. And because there's a transfer of electrons, I will have a cation, which is formed by my metal. I will have an anion, which is formed by my non-metal. Okay, so this is the first thing that must come to your mind whenever you think of ionic compound. The second thing you need to think about is whenever you think of ionic compound, it is about really a metal reacting with a non-metal. Okay, although I did mention here, but I just want you to, at a first level, you must always remember that for ionic compounds, it must always be between a metal and a non-metal. Then, of course, the next question is, metal can be ionic? Answer is no. Non-metal, also no. Okay, so ionic bonding is really between a metal and a non-metal. Okay, so let's look at this now. Sodium atom, chlorine atom. So during ionic bonding, what actually happens? This part here, which we have gone through, will actually happen. The metal will form a positive ion. The non-metal will actually form a negative ion. Okay, so how do they form? Is because the sodium take the electrons, give it to chlorine. Okay, the chlorine willingly accepts it. So they actually form the Na plus ion and the Cl minus ion. So this is the drawing that we want to see. Every time when you see, we always say draw the dot and cross diagram. Okay, this is what we're looking at. Now, I just want to take note, in the middle here, please don't draw this big circle here. In the middle, it should be Na, and maybe it's a different color. In the middle here, it should be Na. In the middle here, it should be Cl. So we tend to remember, write the chemical symbol in the middle whenever we are drawing this kind of bonding diagram. Okay, we call it dot and cross diagram. Now, what if I've got magnesium chloride. Okay, for magnesium is 282. Chlorine is only 287. So magnesium is going to lose 2 electrons. Chlorine can only gain 1 electron. So what happens here is this. Because each chlorine can only gain 1, but my magnesium is going to lose 2, right? So I need to compensate with 1 more chlorine atom. So 2 chlorine atom actually reacts with 1 magnesium atom. So in the process, you can see here, the magnesium loses 2 outer electrons, and I form Mg2 plus. The 2 chlorine atoms, each one gain 1. Right? Each one gain 1. Hence, I get my chloride ion. So Cl minus, Mg2 plus. So Cl over here, Cl over here. Okay, so look at this diagram over here. What they say here is that the electrostatic attraction holds the magnesium and chloride ions together. So because this is plus, this is minus, so there's an attraction over here. And maybe I use a different color. To show the attraction, let me use pink. Okay, so there's attraction over here. There's attraction over here. Okay, why? Because one of them is a plus, one of them is a minus. This guy's a plus, this guy's a minus. So as long as they're opposite charged, they will have that plus and minus thingy over there. Okay, opposite charged, sorry, they will have the attraction over there. Okay, so this is the dot and cross diagram. Now, before we go into the chemical formulas, I want us to do a little bit of practice. So next, let's try a little bit. Okay, so I'm going to show you how to go about doing the dot and cross. So example we're going to have is Mg. Let's say for example, I got aluminium with fluorine. Okay, aluminium is Al1327. Fluorine is F919. Okay, so when aluminium adds to fluoride, I actually get aluminium plus fluorine, I actually get aluminium fluoride. So what's the chemical formula for aluminium fluoride? Okay, so Al1327, right? F is 919. So first thing, okay, because we're gonna do bonding, I will focus actually on the electrons itself. So aluminium, because it has 13 protons, it will also have 13 electrons. So E is 13. Fluorine, I got 9 electrons. Okay, E is 9. What's the electronic configuration for aluminium? Is 2, 8, 3. So I'll start with number of electrons. Next, I'll go into E config, electronic configuration. This one will be 2, 7. Next step, remember bonding, the key idea here is actually to the key idea is actually to make sure that my valence shell is fully filled. So for aluminium, because it's a metal, okay, if you look at it, bonding number is 3, right? So it will actually lose 3 electrons. I'm going to get 2, 8. So this is the electronic config for the ion. This is actually the electronic configuration for the atom. So you lose 3 electrons to form the ion, and this is actually Al3 plus. For fluorine, right, is 2, 7. Obviously, if you don't see periodic table, you also know that it will gain 1 electron. It will become 2, 8. This is actually my F minus. How exactly to draw? Okay, so Al3 plus actually is Al in the middle, 2, 8. So 1 circle, 2 circle, 2 in the first shell, 8 in the second shell. And square bracket, 3 plus. F minus, so I draw F, 2, 8. So take note, because the metal is ready, I use cross ready. This side here, I'm going to use dot to represent, to show that the electrons are, the electrons belong to different places. Okay, square bracket, minus. Now, at this particular point, before you continue, once you have drawn this out, you must always now do the next check. Minus 3 electrons, so the 3 electrons go somewhere else, right? Gain 1 electron, you realize you haven't showed that which electron is gained from somewhere else. Therefore, I must convert one of the electrons to a X to show that it's gained from aluminium. Now, aluminium, I know, lose 3 electrons. Each fluorine only can gain 1. So, our balance, this guy lose 3, this guy only gain 1. I still got 2 more electrons go where? So therefore, 1 aluminium cannot only possibly react with 1 fluorine. Okay, in actual fact, 1 aluminium will react with 3 fluorine. So I need you to put the 3 over here to show that 1 aluminium reacts with 3 fluorine to give you 3 fluoride ion. And because of the way how I'm drawing it here, okay, this is letting you know that when aluminium bond with fluorine, okay, 1 Al will match with 3 F. So my final formula is AlF3. This 3 actually goes to over here. Okay, so I'm going to underline it. This 3 actually went over here. Right, this is the chemical formula AlF3. Because 1 aluminium reacts with 3 fluorine. Okay, this is the dot and cross diagram. This is the chemical formula. Now, I want to go through another example. Let's use another one. Maybe I don't use aluminium fluoride. I use, this case now, I use maybe sodium oxide. Okay, sodium plus oxygen. Okay, actually you get sodium oxide. So I need to draw sodium oxide. So Na 1123, O8 16. So sodium is 281. Oxide is oxygen is 26. So this is going to lose 1 electron. It's going to become 28 Na plus. This guy here is going to gain 2 electrons because I want the outer shell to be fully filled. It becomes 28 O2 minus. So these are the basic steps. Okay, this is the basic step you must always go through whenever you are doing bonding. Once you have gone through this working, actually you'll be able to draw it easier already. So first one I'm going to draw is Na. Na is 28. So 1 circle, 2 circle. So 2, 8. And because it's a plus, so I must draw a square bracket and put a plus over here. So the square bracket and plus, remember, is only for ionic bonding. O2 minus. So O here, 2, 8. So 1 circle, 2 circle. I've used cross for sodium. So I'm going to use dot for oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Square bracket, 2 minus. Now, as mentioned, because oxygen has gained 2 electrons, so therefore I must convert 2 of them into a cross to show that it is gained from somewhere else. Okay. Next up, focus. Sodium lost 1 electron, but oxygen gained 2. So how can oxygen gain 2 when I only have 1 sodium? Okay, how can oxygen gain 2 when I only have 1 sodium? So therefore, to make sure that the electrons balance out, 1 sodium will lose 1. Hence, I will need 2 sodium to react with 1 oxygen because each sodium only lose 1 electron. Okay, therefore, the formula for this fella is actually Na2O. This is the chemical formula. This guy here is the dot cross diagram. Okay, so this is the drawing of your ionic bonding for your dot and cross. Okay, now in terms of the chemical formulas, okay, I think I'm going to pause here for now. Okay,